So friend, we are into the second week of sensor and data acquisition system, and we will see in this lecture specifically sensor and their application areas. Of course, I will not be giving complete picture because it is not possible to cover, but then I will give you hint, and probably you will be pretty confident if you want to explore this area, that is sensor application areas in PHM. Okay. So let's say what are the general point that we want to sensors from the point of this lecture can be defined as hardware or digital sensor, or biological sensor, because sensors cannot be put into one category. There are sensor which are dedicated to electronics, there are some sensor mechanical class, and there are other biosensors. So, and there may be many more classes depending on the application, but that is these areas we will be talking about, and how the sensors have evolved over a period. So, evolution. Sensor technology has evolved from classical devices like level, pressure, flow, humidity. Earlier we used to do level measurement by dipstick, and then transmitter came, and then now we have advanced system, laser based monitoring, and there are MEMS, micro-electromechanical components systems, and then NEMS also. This is a new entry. NEMS means Nano-Electromechanical systems. Okay, so MEMS and NEMS, these two are there. And communication technology, that is DAQ, data acquisition system. This has evolved from wall-based technology in 60s and before to then relay-based technology, and then we had and of course they were all analog actually, and then digital technology which entered somewhere late 70s or 80s, early 80s, and then now we have this because software availability is there, advanced microchips are available. So digital technology has been evolving very fast, and along with that it is supporting the internet of thing, that means cloud connection of the data, and then WSN network, wireless sensor network, and then many more advances which is coming in, and these are the things they are making the prognostics. Actually prognostics, the term has been derived from healthcare discipline, and you will find healthcare even today they are using it extensively actually, and now there is a special effort for engineering system through PHM. And then domain specific, every PHM will have its own characteristic. It's not like one for generic component, pump, valve, pipeline, it is there, but domain wise, like nuclear domain, chemical domain, then we see aviation, then we'll see. So every domain will have their own requirement, and PHM sensors have to be developed for each domain because there will be some specific requirements, whether it might be related to climate, it might be related to vibration, So PHM requires a specific, other than the general areas, it will require to have a look to draft our specification in the domain areas also. And then background and definition is like this. How we define sensor? We know that sensor senses, communicates it to transducer, and finally data acquisition system. But systematically, a sensor is often defined as a device that receives and responds. It receives some input and or some output, that is it responds to a signal or stimulus. It could heat could be a stimulus for temperature sensor, okay, and for human it could be watching is a stimulus, could be a stimulus, smelling could be a stimulus. So like that, like in engineering, hardware, and at human level also signals and stimuluses they are applicable. The stimulus is the quantity, property or condition that is sensed and converted into electrical signal, often through transducers. So probably when we study this topic, this definition should be well understood and should be by heart to us, so that we can work on other things. Modern scope is we have the NEMS, MEMS, and so many advanced technologies where all sensing, right from sensing to decision making or actuation, it happens on a microchip. Okay. So thanks to semiconductor devices and their advancement, so integrated chips are there where all the functions are developed right from sensing to actuation. Actuation could be starting a pump, it could be actuating some relay or whatever. So mechanical thing, and they are all embedded onto the one system. Okay. And then we have the stimulus like optics, heat, load, heat, load is mechanical, impact, motion, humidity, pressure, etc. And the output depending on the sensor signal that is converted to optics like on off or value, whatever function we are doing, electrical or mechanical or electronic function. So now human sensors are very important. They are entirely different than our normal sensors that we use. They are embedded onto our body, and then we should be able to get signal from our surrounding, and that those kind of stimulus could be heat, light, sound, vision, image, smell, pressure, emotions. In fact, the humans, though they don't have very strong indicator for emotion, but we get the emotion right, and that is something much beyond than our this 5 sensor: eye for vision, ear for sound, nose, smell, tongue and taste, and skin for touch or cold. So apart from this, the emotions, they are playing out at the level of mind, and if we ask an expert what is emotion, it is a chemical process which is partly it is understood. It is happening at the neuron level. We will discuss as part of human factor, or maybe in my previous lecture you will find this discussion, how emotion and how they drive us actually. These things are like something mounted on our system, but then converting, if eye is watching something, what perception is formed, that is more important. If we are hearing a sound, I am listening to music, it gets converted into complete emotion, liking, disliking, starting from liking, disliking to getting highest sense of the music. So the emotion drives all this, the input for those emotions, they come from this root. Somebody touches us with love and we feel happy, so those are the things, and so these are a special element of human factor, and they often determine our performance or our life, how we move around actually. And then there are some major processing component at the level of brain that I was talking about, perception followed by decision making and actions and all that, and kind of communication which is happening from our brain to the rest of the body through a nervous system. They are a special area in itself, So now let us see typically, we are talking about sensor and all that, what they sense and what are their application. Okay. So like electrical sensors will have voltage, current, frequency, resistance. In fact, I am repeating it here because this is something a different connotation I am talking about here after talking about humans and all. The chemical sensors, pH, conductivity, turbidity, concentration, elemental analysis. Mechanical sensors, load, stress and all this diagram, velocity, acceleration. Now we are measuring the velocity and acceleration, but again the same technology is used for like accelerometers. They are used for vibrations. Okay. So infrared sensors, remote operations, I could see one only. Maybe detection also we can say something. Then hydraulic or pneumatic sensors, flow, pressure, temperature, torque, etc. Electronic sensors, we have temperature. So nowadays most of the work is done by electronic sensors only, and we have various attributes over here. Metal oxide semiconductors, sensors. So these are gas detection, air quality, leak detection, quality and control of food, automotive exhaust, medical diagnosis. So these are very sophisticated. In fact, you can say they are sort of a MAM, micro-electromechanical component, but they don't have they are only a sensor alone. They are not having any actuation mechanism. Sensor is a MEMS is a complete solution in itself. My car door is I am locking and there is a MEMS sensors are used. So it gives a signal to my dashboard also, control board also. Door is locked, door is not properly locked. So MEMS sensors are used most of the advanced systems actually. Thermal sensor, again temperature, this thing. And then neutronic sensors, neutron flux, alpha, beta and gamma radiation, biosensors, glucometer, optical thing. In fact, some of the things feeding to themselves. If I talk about the human body, glucometer, optical, electrochemical sensors, they are used. Ultrasonic distance, even diagnostics of human body, ultrasonic methods are used. For engineering also, if any defect is there, or healthiness of the pipeline or passive system, and then optical sensor, LED and laser sensors. Okay. So these are the list is not exhaustive. Let me mention specifically. There can be many more sensors, but these are the things. Some of the things I have and what are the important properties which can form part of our decision making. So these are, I would say, metrics. So these are important. Accuracy is nothing but closeness to the true value. In fact, in one of these lectures, I have defined a mathematical expression for this confusion matrix. Through a confusion matrix, how we define, I think, precision and accuracy, these two parameters. Precision is nothing but how close we operate to the measurement value. Range and span. The sampling, you will say, what we are measuring, to what range we are doing this measurement actually. Okay, what is the coverage we have, and maximum and minimum value of our measurement. In some sense, it is called uncertainty also. And the linearity, any sensor we make. So that is where we have to be very particular. When we buy a sensor, whether it will fit into my application. If in my application, the temperature is ranging from let us say 20 degrees centigrade to 160 degrees centigrade. So in that domain, the characteristic should be linear, because material doesn't have a linear characteristic all through, but in that domain it should be linear. That means proportional linear line should work out for measurement actually. Hysteresis, it is the difference in output when we put varied input in two ways or increasing and decreasing order. You would have seen hysteresis curves actually, knowing it. Sensitivity is what is the change in the sensor output related to the change in the input. So ratio of input output, that will tell us sensitivity. Okay. And then resolution. Resolution is the smallest change in the input that can be sensed. I mean, we require, we will say, highly sensitive sensor. So we are talking about resolution. Reproducibility, it should not repeatability. They are very close to each other. We should be able to reproduce the results here. What we did for the same condition, we should be able to produce. And repeatability, it should not change when we do different measurement. And this is, of course, response time. Time constant, I put it actually. So how it should be. The response time should be such that time it takes for sensor's output to reach a specific percentage, of its final value, and after a sudden change in the input. That means it should respond pretty well to the changing condition, and it should reach 95% very efficiently. It should not take time. It should not have its own time constant for reaching the true value actually. Like I see in a car. If my car is, if I increase the speed of the car, it takes some time to reach there. But then all the other systems, they may not like that kind of response time. They would like to go. But since inertia is very high, instrument has its own time constant. So we are happy. Normally we don't complain. Okay. But otherwise, the response time should be very high for a given application. Sensor for IoT is a very special area, Internet of the Things. It is not wired. It is basically communicating through the cloud, and this is an era of internet, where you are operating in two domain, frequency domain and time domain. Okay. So radio frequency identification community coined a phrase of Internet of the Things that that needed special attention dealing with storage and communication of data, because now data has become one of the central consideration for our growth or our operation or our system or for societal system. So huge data centers are being developed, and this is being made possible through Internet of the Things. And for us it is important because failure of Internet of the Things or any compromise in Internet of the Things will compromise our PHM quality actually, because we are saying we are monitoring sensor is put in the area where we are monitoring, and we have the control room where the readings are available. So those things should be reliable. There should not be any loss or distortion. So that is where the role. And objective was to improve the quality of the detection and communication. Okay, sensor special efforts have gone into development of sensor through Internet. Okay, it's okay, well known fact. Constituent component. There are components like first is sensor like from cloud depending on the requirement, acoustic, humidity, temperature, physical location. These are the things that are monitored, and communication protocol RFID, Bluetooth transducer, and power management. These are the essential feature that should be there. Probably you must be getting this idea. If I put some sensor, it should be autonomous in the sense that it should have its own power management system, it should have a data management system, and it should have a diagnostic system also, local diagnostics it should be able to do. So that is the kind of expectation that we put on the sensor application. IoT is at the core of domain. It is any industry, service or location that we use, IoT as governing us. Okay, and here is the importance of the IoT in autonomous diagnostics, making sensor relatively self-standing even in the remote areas actually. Now, for given parameter or application, there are some sensors. You will get it straight here. Vibration, you have a uniaxial accelerator, because vibration you monitor can monitor on one axis also, and you can X, Y, Z, three axis. So triaxial and uniaxial. If we use only uniaxial accelerometer, we will be using, let's say if it is X oriented to X, Y Z dimension will be missing. So for a complete information, we should use triaxial sensor, that is information coming from X, Y and Z axis. And there are sensors put on the sensor assembly. And then temperature, we know there are thermometer, then thermocouple, thermistors, resistance temperature detector, and semiconductor based devices. These are the technology. Which technology suits? And I said linearity. For my measurement domain of interest, I should have that area where the things should be linear, proportional increase or proportional reduction. Okay, and then humidity, hygrometer, capacitive, conductive, resistive, thermal, conductive. So these are the technology that are there. Dust, we know that optical, laser based and attenuation based technologies are there. Concentration, ultrasonic in water, it works very well, and molarity based, this is lab based things actually. Voltage, capacitor voltage and resistive voltmeter. Current, you know that Ohm's law and all you are measuring. Power is inductive, direct, and these are the technologies that are available for. So we want what kind of sensor we want for measurement of power. Okay, that we can decide based on our power loading, that domain or the range that we want it. And then strain gauges, flow, we have so many devices, Venturi device, very traditional thing, and then electromagnetic, sensors, turbine sensors, ultrasonic sensor, and each of these sensors are having their own special application. And sometimes you cannot manage other sensors, because in some sensor, if it is required turbine like switch, it is a direct thing that we are measuring over here. Ultrasonic, where we can access, but it should not be interfere with the other signals. Mass flow, thermal, these are the technologies applicable in different area, different domains, where they have their own advantages. Pressure, altimeter, strain gauge and barometer. So we have seen the first thing, different type of sensors. Again, I am repeating here, the list is not exhaustive. We will talk about the vibration sensors. As I mentioned, that we triaxial accelerometer, they have X, Y, Z. 3 sensors are put in. See, you can see here, and one. So here the sensor will be connected, and otherwise you can use, if we don't have the application, uniaxial accelerator also you can connect. Advantage is, apart from multi-axial measurement, data collection is faster if you have a triaxial sensor. And then internal details of the accelerometers we are not able to see, but I will try to explain the basic concept here. What is the principle of operation? So here we have a quartz or piezoelectric crystal, and when you apply a load, okay, here from the material generates a current because of electrons gathering at one location, and that generates a current, and that is sensed by it. So you saw one mechanical a base plate is there, mechanical load applied here, seismic mass we can say, let us say, if we are going into the seismology and all, and that will give us a current, and that will tell us what is the acceleration or velocity, whatever you are monitoring actually. And this is a electrical side of this thing, and the motion of a vibration is x axis over here. So this figure is for uniaxial, but actually if 3 sensors like this are embedded into it, it becomes a triaxial, and their integration is required. MEM sensor, you know, they are microchip sensor in nutshell, and that can be MEMS or NAMS also. Okay. And the MEMS sensor, when sensor is designed, manufactured using MEMS technology, then it is called micro machined micro sensor, or simply MEMS sensor. MEMS sensors perform, apart from sensing and processing the information, the final action using the device embedded. So what is the first? It is a MEMS optical sensor we are talking, and then we have conversion unit, ADC, analog to digital conversion unit. Then there is an integrated chip which is called controller. You can do controlling operation over here, whatever comes from the sensor, and then diagnostics, implementation, you know, and then MEMS output contacts, and then electrical system actuation. So right from signals to actuation, we MEMS sensors do on board actually. Okay. So this is a simplified representation of MEMS. There are many complex components. Okay. And then yeah, we can see in this week we have seen introduction and background for the sensor systems alone, and hardware and human sensors and role of stimuli, major categories of prognostics and health management sensor, vibration triaxial sensors, introduction to. In fact, if I have to say what is the gist of this particular lecture, that is 4.2, is this, that mostly for mechanical components we require temperature and humidity, especially when there is a relative motion, you know. So this kind of sensors are required, and 80% of our problems will be solved. Suppose if it is a passive component, then we have to detect the crack and all that. So that sensor spread across the length and breadth of the plant, it will send information to us regarding health of the component, which is in traditional sense it is called in service inspection. Okay. And then vibration is one thing. Then we have various degradation mechanism. So how I will measure the corrosion rates. Okay. So how I will measure the fracture property. So again, if I talk about the fracture and risk assessment, the uncertainties are very high in fracture risk assessment. So the kind of technology, so I am giving one input here, that implementation of PHM requires R&D component, because this technology is still at very advanced labs like aviation or space, and or it is in the lab space. So we cannot implement a PHM technology. A laboratory is required, or a consultant is required who has deep knowledge of degradation, sensing, and converting into the electronics, that kind of the information is required. And of course, at organizational level also, the management system which is now having a tangentially different system for maintenance management if you compare with our traditional approaches.